Hi, student and everybody, Cook's Radio. Today is Thursday, 7th of March. What I'm going to do today is I'm going to talk about our terminology or some technical terms. In this one is going to be about our semiconductor. My objective is I'll not only try to explain about our terminology that the student have learned that before, and then I also speak in English in case that some people want to practice English. What I did is that I put a bracket just for this one. So when you want to say this word, what English word you're going to use, so I put like this one, obey, or namely, that's for the name. So let's get started. For energy band gap, or you have like conduction band and also valence band, right? And the separation of the conduction band and valence band is we call our energy band gap. The difference between the conduction band and valence band is called energy gap. In general, is about 1 electron volt, which is a very small energy. And for semiconductor, for semiconductors, that's 1 electron volt. But for conduction, it's always conduct, right? So energy band gap is about 0 electron volt. For insulator, of course, the energy band gap is become a larger number, so that's about 6 electron volt. The next one is the Heisenberg uncertainty principle definition. The Heisenberg uncertainty principle, that's called uncertainty of Heisenberg, or uncertainty principle, that come out on 1977 by a German physicist named Werner Heisenberg. Straight that position and velocity of any object cannot be measured at the same time. Even in theory, the way of thinking of position, exact position and exact velocity together in nature, it has no meaning. Alright, that's the Heisenberg uncertainty principle definition. The next one is the Fermi-Dirac distribution function. You probably get used to this, especially for electronic engineering. The Fermi-Dirac distribution tells about the possibility to occupy a state, a certain state by a fermion, and you have equation, the Fermi-Dirac distribution function does depend on the energy equal to 1 over 1 plus exponential E minus EF. EF is the Fermi level, and divided by our KT. K is the Boltzmann constant, and the absolute temperature in the unit of Kelvin, you know that. Okay, EF is the Fermi energy. Fe tells about the possibility of particle to be in any state that corresponds to energy E. And for the physics fermion definition, you're probably wondering, what is the fermion? In particle physics, fermion is a type. Okay, now you know that how you're going to use English for this type word of particle that obey statistical law of Fermi-Dirac, namely Pauli exclusion principle. These fermions still have a quantum spin that contains half integer. For example, one and a half minus 1.5 minus 3.5 and so on. By comparison, there's still other types of particle that's called bosons, which have a spin to be integer number. For example, 0, 1, minus 1, minus 2, 2, etc. Now, what makes a fermion so special? Sometimes we call fermion as the matter particle, because it's the particle that composed or make up from the thing that is the physical matter in our world, including proton, neutron, and electron. Fermion first predicted in 1925 by physicist Wolfgang Pauli, who tried to figure out, okay, this one is figure out atom structure proposed in 1922 by Niels Bohr. Bohr used the experimental evidence. Okay, this is the word for Thai word. Experimental evidence to create atom model which contains the electrons, create orbital or stable orbit for electron to move around our nucleus of atom. Even these are match well, okay, this is well with evidence, but there's still no particular reason which show this structure to be stable, and that the explanation for which Pauli tried to reach. He realized that if assign a quantum number, which is later is called quantum spin for these electrons, seem to be some sort of principle, which means that no two electrons are to be in the same state, and this law turned to be known as the Pauli exclusion principle. In 1926, Enrico Fermi and Paul Dirac independent each other to try to understand other aspects of electron behavior, which seem to be contradictory. Okay, this is contradictory. In doing so, uh, uh, they attribute statistical way to be more complete to dealing with electrons. Even Fermi had first developed the system, but they are very close enough, and they were enough for posterity to has the double statistical method for them. Our statistical Fermi Dirac are say that even particle itself is named after Fermi, for the name of Fermi. The fact that the fermions cannot collapse in same state again, this is their ultimate meaning of Pauli exclusion principle. This is very important. Fermions within the Sun and another planets or planets is collapsing under their intense gravity, but they cannot collapse fully or completely because their Pauli exclusion principle. As a result, there is the pressure which push collapsing the gravity of matter and planets. Is the pressure that create the heat from the Sun, which the fuel is not enough, but is the fuel of our planet. But there's still a lot of energy in the rest of our universe. That include the creation of heavy elements, as explained by our stellar nucleosynthesis. The next one is about the fundamental of fermions. There are 12 fundamental fermions. Fermions that not composed of a smaller particle, and thus is identified from experiment. They are divided into two categories, which are quarks, is the particle that are composed of hadron. There are 6 types of quark. That's the distinct, which are up quark, shram quark, top quark, down quark, string quark, bottom quark. Leptons. There are 6 types of leptons, which are electrons, neutrino, muon, neutrino, tau, neutrino. Beyond these particles, the theory of equation of supersymmetry predict that every boson will have a fermion counterpart that cannot be detected because there are 4 to 6 fundamental boron that suggest that if supersymmetry is true, there's still a fundamental fermion from 4 to 6 thus cannot be identified. Presumably because it's highly unstable and decay in another forms. Beyond fundamental fermion, another set of fermions can be created by combining fermion together. This is possibility with boson to have a particle that are from half integer spin. Quantum spin add up. So basic mathematics, basic mathematics show that any particle that has the number of fermion as the even number, will end up with the half integer, and so it's going to be fermion itself. Some example includes baryons. These are particles like proton and neutron, which are composed of 3 quarks joined together. Since each quark has the half integer spin, the result of baryon will have a half integer spin always. It doesn't matter what quark 3 they will combine to form a structure. Helium-3 composed of 2 protons and 1 neutron in nucleus, along with 2 electrons that are circling because there are even number of fermion. Resulting spin then being half integer, which means that helium-3 is the fermion as well. Okay, so hopefully this is something about terminology, and then you can practice, by and then recall the definition of each of them. I will do more, later on. Okay, I'm not feel very good. Seem like catch cold or something. I'll see you later. Goodbye.